Hi everyone, so my name's Shane and today I'm going to be talking about commercial off-the-shelf FPGAs in orbit, so putting them into space. So in 1912, Victor Hess, a famous Austrian physicist, performed some experiments. He wanted to see how ionizing radiation changed as you increased in altitude, so as you went up. So he got a hot air balloon and like a radiation counter, and he took off into the skies. And initially, the assumptions that everyone had was that the further away from Earth you got, the less radiation you had. So the radiation was coming from the Earth. And he found this to be true. So initially, as he was going up, the ionizing radiation fell off. However, he reached a point then when it started to increase rapidly. Hess concluded that a radiation of a very high penetrating power must enter the atmosphere from above. And he was right. Cosmic rays from space do penetrate our atmosphere. And more than that, high energy particles emitted from the sun get trapped in our magnetic field or enter the atmosphere and can cause real problems with our electronics. A lot of this radiation gets trapped in the Van Allen belts, so the Van Allen radiation belts, and causes things such as the aurora borealis. But it's a real concern for any sort of electronics that's working at altitude. So in computers that are on board planes or on board satellites, they need to really take this into consideration when they're designing their systems. For this reason, a lot of avionics and satellite computers are really conservative. So generally they're processors that run at 25 megahertz incredibly slowly. Oftentimes the instructions are triplicated so that they can make sure that it definitely worked correctly. And generally, onboard satellites, you just do not have very much compute power at all. Now, that is starting to change. People are starting to question whether we need to be that conservative all the time. And there's this European Space Agency mission called OPS-SAT, which is trying to test commercial off-the-shelf components in low Earth orbit. Now, one of the surprising things about OPS-SAT is that, it's a cheap CubeSat. It's like 30 centimeters by 10 centimeters by 10 centimeters. Yet it's 10 times more powerful than anything else that's flying in ESA's fleet. And the reason for this is because it's not using those super conservative, space-hardened processors. It's using commercial off-the-shelf stuff. So, the FPGAs that are on board have little ARM cores in them that run at 800 megahertz, and they boot Linux. So you can actually connect to Linux on the satellite, which is something that's not really heard of in space applications. This is an overview of kind of the different components on board OPS-SAT. Don't worry, I don't expect you to be able to read each of the components. I'll kind of go through them. But the big kind of picture is that you actually have two CubeSats here in one. At the top there in the green is the ESA CubeSat, and this is a very conservative, traditional, very fault-tolerant setup, traditional satellite setup that ESA controls. It even has its own dedicated communications. The blue stuff down at the bottom is then the experimenter satellite that experimenters have access to, and this is where all the commercial off-the-shelf components come in. And so the ESA CubeSat kind of keeps track of the experimenter's experiments, and if anything starts to go a bit of haywire or anything like that, it scrubs the experiment. And so on board the experimenter satellite, which is what we have access to, there'll be a couple of FPGAs. So I think you have access to two FPGA boards and the ARM cores that are with them as well. There's a high definition camera, so this would be good for if there's any collaborations with the Swansea Vision Group. Maybe we can do some onboard kind of image processing. There's a software-defined radio, so you can actually pick up amateur radio bands on this thing, or IoT kind of communications using a software-defined radio. There's an optical receiver, so they've got some experiments where they're trying to uplink data to the satellite via laser. And there's the fine ADCS. So you can actually, and what that is it's a bunch of kind of flywheels, inertia wheels, and magnetotorquers that you can use to orient the satellite. So part of the experiments could be like a control system for keeping the orientation of the satellite right. And so they give this access to the experimenters to use, which is pretty amazing, really. But what I'm interested in particular is the FPGA boards that are on OPS-SAT. And so I've formed a small group. It's very early days yet, so we're still trying to figure out a name for a group. At the moment, we're just Swansea University OPS-SAT group, which has actually proposed kind of a proposal to ESA to ask for some money to work on this as well. It's myself and a bunch of undergraduate students, very, very good undergraduate students who are doing projects with me as well. And we're also collaborating with 2 companies. So there's Stoffel, who some of you might know of because they're involved with the CDT and things like that. And they work with IoT devices. And we have kind of a cool application that I'll talk about in a while. And Accelera, which is then an FPGA startup company. So in this talk, we'll be looking at FPGAs in space. So using the FPGAs on board OPS-SAT, in particular commercial off-the-shelf FPGAs. I'll start by talking about why it's really desirable to use FPGAs in space. And I'll give a brief overview of what an FPGA is as well, for those of you that aren't familiar with the work that I do. Then I'm going to go on to the dangers. So obviously, because of these high energy particles, there are issues with using FPGAs in space. And so in particular, FPGAs are pretty sensitive to these, and so we need to be aware of them, designing them. And then I'll talk about some research ideas that me and that group of students and Stoffel and Accelera are planning to do on board OPS-SAT. So let's start with why FPGAs are good, and I'll start with an explanation of what actually is an FPGA. So an FPGA is reconfigurable hardware. So I often describe it as the Lego of digital circuits, right? So you can make any digital circuit you want out of it. It won't be quite as high fidelity as if you went to a foundry and got them to make a custom chip for you, custom hardware chip. Like, it won't be able to have quite as low power consumption or quite as low latency, or it won't be able to run at quite as high a clock rate as if you made a custom chip. But you can get pretty close. You can still do custom hardware. So generally how you build hardware nowadays is you actually write something that looks like code. It's not like programming code. It's actually what's called a hardware description language. So you describe the hardware textually, and then you get a circuit out. Now you can either then give that hardware to a hardware description to a foundry and they will make you a custom chip, or you can run it on one of the FPGA devices that I'm talking about. And so FPGA stands for Field Programmable Gate Array. So field programmable means that you can update it once it's deployed. So this is hardware that you can actually change once you've put it in an application. And gate array basically means that it's a 2D array of these universal logic gates. So this is the gate array here. So the basic primitives of an FPGA are something called logic elements. And these are kind of universal logic gates. So we can program these to have any Boolean function we want. The next thing then is a routing matrix, which is also configurable, that says how we connect these different logic elements together. And so we can give the FPGA tools that hardware description, and then the tools will go and it will configure each of the logic elements to be different Boolean functions or different logic gates, and it will configure the routing network to actually connect them up together to make the circuit that you want. And so in a way, ASIC is a custom chip, and then CPUs is kind of the traditional computers that we're used to. FPGAs sort of sit in the middle. So they are hardware, but they're programmable, and so they're sort of in this strange land between hardware and software. And so why are they super desirable for space applications? The first is the performance. So generally hardware is really high performing, right? You can create really parallel hardware for a particular application and make it super efficient. Look at things like graphics processing units, right? They were made for a specific application domain doing graphics and designed such that you could get incredible performance out of them by using lots of parallelism. The same is happening now with machine learning and with Bitcoin and cryptocurrencies. Making custom chips gives you a lot of extra performance. So that's one big advantage of using FPGAs. You get a big performance increase. You also get a big increase in latency. So on a traditional CPU, you might have things like the instruction scheduling overheads, operating system overheads, these sorts of things. And that can really slow down how quickly you can respond to events. With custom hardware, you don't have any of that. So on a satellite, if you're flying overhead and you're trying to respond to your base station quickly, if you use custom hardware, you can make that loop really tight and respond quite quickly. So that's one big advantage. Another one is power consumption. So hardware, because you don't have all the extra, not inefficiencies, but extra overheads of instruction scheduling and all that stuff that comes with making a general purpose processor, you actually get a lot of power efficiency from that as well. So the performance per watt of an FPGA is generally much, much better than, say, a CPU. So for the performance you generally get a lower power consumption, which is very important for space applications, which might be constrained on the amount of power consumption that they can generate from their solar panels. Finally, the last big important one, why FPGAs in particular are very important for space applications, is you can update them once they've been deployed. You can actually change the hardware once it's in orbit. It's very difficult to go up into space and change a chip on a satellite, and it usually isn't cost effective to do so. There's very few satellites where we've actually done those sorts of hardware repairs in orbit, like the Hubble. But generally for most satellites, you're not going to do that. So the fact that you can actually update the hardware once it's deployed is very important. And OPS-SAT's actually benefited from this already. So in the 2-year orbit that it's already been doing, 2-year kind of flight time, it has had some issues with its memory controller. So the ARM chips couldn't access DRAM. But what they were able to do is actually reroute those DRAM signals through the FPGA on board and connect that up to a local DRAM on the FPGA, and they were able to save that processor. They didn't need to waste that processor. Okay. So that's the advantages, but there are big problems with using FPGAs in space, in particular with those high energy particles, and this is why they haven't really been adopted to date. Part of the reason why FPGAs in particular are very susceptible to high energy particles is because of the way they're structured. So we have this, 2D array of logic elements and a routing matrix to connect them together, like I described before. And how we actually configure this is with a big block of SRAM. So there's this thing called the configuration RAM, which is made out of SRAM, the fastest RAM we've got. And you write ones and zeros into this, and you actually configure the logic elements and the routing matrix and how things are connected together. And the problem with memory like this is that when a high energy particle strikes it, it very often causes that bit to flip just because of the structure of the SRAM circuit, but also that effect of the high energy particle gets saved because it's a memory. If you had a processor and you get a high energy particle striking part of the data path, you might get a bit of energy increase for a bit, and a 0 might turn to 1, but it will be a transient effect and it might not get saved. It just depends on how it gets hit. With an SRAM, it's much more likely that that effect of the high energy particle striking it will cause a bit flip that will be saved. And so that's a problem. It's also a problem with that when a bit flip happens in the configuration RAM, it actually changes the structure of the circuit that you've configured. So it's actually structurally changed things. Maybe it's hit something in your logic element and it's changed it from a XOR gate to an OR gate. Or maybe it's changed something in the routing matrix that disconnects an output or connects it to somewhere else where you don't want it. And so this adds an extra level of complexity. You're not just getting errors in your data, which you can probably try and correct against and try and deal with. You're getting errors in the very structure of your hardware changing and morphing with these errors. And so that's kind of why FPGAs haven't been adopted. There's extra sensitivity in the configuration RAM, as well as getting errors in the data that's flowing through. And so we have 3 main experiments that we're kind of proposing to fly on board. Now I'm encouraging the students to propose their own experiments, and there will be more experiments coming in the pipeline that we will submit to ESA to fly. But for the moment, these are the main 3. We've got a fault detection circuit. So we actually want to kind of get a good profile of how many faults the FPGAs experience when they're in orbit. There isn't good data on this yet, and we want to collect that. Then we want to extend some of my PhD work, which is on making tools that will automatically generate protected circuits that can survive kind of the worst kinds of errors on the FPGA device. And then finally, we have this application that we're working on with Stoffel, where we can detect IoT signals in orbit and use to verify the locations of these IoT gateways. So let's start with the first one, which is the fault detection circuit. So I talked about the structure of an FPGA and the configuration RAM. We want to detect faults in a few different places on the FPGA device. I'll only talk about two here, but if people are interested, we can talk more offline. So in first, we have the errors. So when you get a high energy particle strike, that actually upset the configuration, so change the actual structure of the circuit. And so we've got CRAM errors. But then we also have errors actually in the data that's flowing through our hardware circuit. So we want to detect how many errors happen in the register logic, it's called. So as data is flowing through, how many errors can we expect there? And it will be interesting to kind of compare the two and try and find the locations of them. So for the data errors, how we're going to do that is build an FPGA image that is essentially a giant shift register. So a shift register, basically just every clock cycle, will copy the data at its input and shift it along this long snaking circuit. So, you just have this every clock cycle data shifting along this big circuit. And we feed in a known pattern into the input. And then at the very end, we're kind of checking if that known pattern is coming out the other end. And we can see if we've got an error or not. And we can even have these checker units dotted throughout that snaking kind of snaking pipeline to see where the errors are and try and get a location for them. Now we want this circuit to fly as often as possible, so we want it to fly maybe in amongst other FPGA experiments that are on board OPS-SAT. So we're going to make it as configurable as possible so it can snake around other circuits and things like that. The other one then is the actual configuration RAM errors, and we want to try and get a good feel for how often those happen. Luckily, there is error correcting codes and CRC checks built into the configuration RAM that we can periodically scan to see where and when an error occurred. So we're planning to kind of gather data from those. There's some other things as well, such as block RAMs and other things, but I don't have time to talk about that here. And the other thing that we want to do is match when we get these errors with the activity of the sun. So we'll look at data from the Solar Dynamics Observatory to try and correlate if there's an increase in solar activity, do we see more errors? And also get the GPS position of our orbit, because in certain regions of the world, you're more likely to experience these errors. So there's this region called the South Atlantic Anomaly where the magnetic field has dipped. And so when satellites fly through this region, they tend to see more single event upsets. And the reason we want to get that is because that might actually provide operations detail. It's not just that we want to gather as much data as possible, but might also provide operations detail. So when you're flying over certain regions or when there's an increase in solar activity, you dynamically adjust the amount that you're protecting your circuit. And we feel like that's very important information to have. The other thing that we want to do as well is to kind of do ground-based fault injection. So we want to build a little setup where we have the FPGA boards that are on board OPS-SAT and do kind of fault injection to every single configuration bit and see how it affects the outputs of circuits. So I've done this with other types of devices. So I've done it with Xilinx devices, unfortunately not the boards that are flying on board OPS-SAT. And you see some very interesting corruptions in the output data when you do these sorts of experiments. And we were able to determine certain regions that require more protection. Okay. So that's kind of the first bit. We want to kind of get a really good detailed fault profile of the FPGAs on board and do some ground-based exploration of that, but also gather data from in orbit. And this is something that they don't have already and that they really, really want. The next thing that we want to do is to actually make tools that can automatically generate circuits that have some degree of protection from these high energy particles. And some of the data that we collect from the fault detection circuit we think will drive the development of this as well. So it's based around something called high-level synthesis, which is where you take a programming language such as C. C is high level for hardware engineers. Take a programming language such as C and generate a circuit from it. And so if we have something, let's say, like matrix multiplication, where you have, these 3 for loops, and you're doing maybe some big floating point addition and multiplications in the innermost loop, then the HLS tool will generate a circuit that looks like this. You'll have a control FSM, which will control kind of where the instructions are being kind of scheduled to run. And then you'll have a data path where you'll have maybe int add, an integer adder, integer comparator for the loop bounds, maybe then a floating point addition and floating point multiplier for doing the actual calculation. You'll notice that those floating point addition and floating point multipliers are much, much bigger. And so if you want to protect this circuit automatically, generally what you'd do is you would duplicate it or triplicate it. And so you would create two versions of this circuit, and then you would implement very complicated checking logic between the two to make sure that both of these two separate versions of the circuit were executing the exact same thing every single cycle. However, this is super expensive. Duplicating the entire circuit both consumes an awful lot of resources on the FPGA device, but also an awful lot of power. What if instead we protect the most important bits, and what if we use the high-level description of the circuit to try and figure out what those most important bits are? And so that's what a lot of my PhD was focused on. And so I developed this tool called StitchUp, which was an automatic pass that will protect only the control flow of the circuit that's generated. So in the matrix multiplication value, if we have an error in one of those for loops, then we potentially could get stuck in an infinite loop, right? That's quite bad. However, if we have an error in the floating point units, then we might get an incorrect value or a slightly incorrect value, which is arguably less bad. It depends on the application, right? So if you're doing something like machine learning or video compression or something like that, you might be able to tolerate some errors in your data path. So with StitchUp, what it does is it extracts all the control flow operations and anything that touches control flow operations, and it creates a control flow replica. So for the matrix multiplication example, it just pulls out all those for loop bounds and it generates a circuit for it. And what often happens is that those control flow replica circuits are much, much smaller than the full circuit. So, generally they only use integer adders and comparators for calculating the loop bounds. The other thing as well is that we can super easily actually compare the actual, the checking logic becomes much simpler as well. And so we actually end up saving an awful lot of area while protecting automatically against the worst case of errors. So we want to try and implement this in the tool flow of OPS-SAT so that we can actually generate control flow protected circuits on board. But we also want to extend it as well to give the user some ability to protect parts of the data flow. So we plan to add critical kind of type annotations to the input source that will allow the user to say, this is a critical part of the circuit, replicate it. And then we can selectively replicate that part of the circuit. Okay, so that is sort of the tooling side of things and how we're planning to generate tools. And the next part is an application that we want to build using the tools that we want to create. Okay, so the application is to make to use the software-defined radio on board OPS-SAT to detect kind of radio signals from Earth from these LoRa Internet of Things gateway nodes. And so we're working with Stoffel, who are working very closely with Helium that use this technology. And so what Helium's trying to do is to actually create an Internet of Things network infrastructure, but they don't want to build it themselves. They want to incentivize everyone to do it. So people set up these Internet of Things gateway nodes, and they get incentivized to do so by getting some cryptocurrency. So they get rewarded for doing this. And when people use their network, they get extra rewarding and things like that. The problem is that Helium, it's really essential that Helium knows the location of these nodes and that it's verified. So, you don't want someone spoofing their GPS data and saying they're somewhere where they're not and these sorts of things. So what they use currently is other Helium gateway nodes to verify the locations of other Helium gateway nodes. However, what we want to do is to actually use the software-defined radio onboard OPS-SAT as it's flying overhead to verify the locations of these IoT gateways. So it's been proven that OPS-SAT can pick up these signals. Not necessarily the Helium ones, but they have used it to detect LoRa signals, these IoT kind of networking signals. And so we want to pick it up, get the software-defined radio data into the FPGA, then decode, build decoding logic and kind of helium packet detectors in the FPGA fabric using those tools, making sure they're fault tolerant, and correlating it with the GPS data on board OPS-SAT. We'll then store it, and then when we fly over a downlinking station, downlink it and use that to verify the location of these IoT gateway nodes. So that's kind of an overview of what we want to do. There's a lot more ideas we have. So, looking at RISC-V processors and trying to make them fault tolerant and making fault tolerant compilers for the RISC-V processors and things like that. But kind of we can discuss more about that offline. And if anyone wants to collaborate on it, that would be great. But we have 3 main missions that we want to fly on board this OPS-SAT protocol. This OPS-SAT project. We have a fault detection circuit to try and get as much information on the amounts of faults that these FPGAs experience in orbit. We have some work on some automatically protecting tools so that we can automatically protect against the worst kind of errors or leave the programmer define what regions of the device they want protected. And we have this cool application where we're verifying these IoT nodes in orbit. So that's the end of the talk. Thank you very much for listening.